when I was actually rotating through one of the Harvard-affiliated hospitals. I came across a 28-year-old woman who had a heart attack. And I said, wow, very young. How come? Oh, she has poorly controlled diabetes and high blood pressure and cholesterol.
If you go by that design, Indians are not fat. Fat means contextually fat and obesity goes hand in hand. So we are not fat, so that means we are fitter. But interestingly, we are not. So how much is the weight of the fat in the body is actually linked to the health of the body.
Pointing to another important marker, BMI, in your 2-3 days in India, you would have noticed that there is this standard Indian male has a nice belly here, right? How do you look at the BMI thresholds for South Asian populations versus other populations?
Yeah.
Hello, welcome to the Biopeak podcast, brought to you by Longevity India, where we discuss components, mechanisms, and tools to help manage your health span and improve your longevity. I'm Prashant Prakash, and I have with me my co-host Deepak Saini, and we have a very special guest today in Sue Anne Toh. Sue Anne is someone who has worked across the globe in multiple health systems in the US, in Europe, and in Singapore. And as a clinician scientist, Sue Anne, I don't think there's anybody better than you to help us in this masterclass. So in this very first episode, we will cover what is metabolism and hopefully dive deep into the aspects that drive and govern the processes that govern metabolism. So start out a little bit by uh, uh, your background. So a little bit on your background, and especially as a founder and CEO now of NOVI, which is an integrated health startup.
Thank you. Thank you, Prashant and Deepak, for the invitation to join you. I think this is a great platform, and I look forward to sharing a lot of the developments in this area. As for myself, I am an endocrinologist. That's a specialty in medicine that deals with hormones and metabolism. I went into that somewhat accidentally, I suppose, because I grew up in Malaysia. And I had never really wanted to be a doctor, but was somewhat fueled by an episode where, as a little girl, my grandmother had a heart attack. And so that inspired me to think about perhaps being a cardiologist. After all, heart disease is the number one
Right.
killer in the world. And I suppose as a person, I've always been curious and interested to solve meaningful, big problems. Along the way, when I was actually rotating through one of the Harvard-affiliated hospitals, I came across a 28-year-old woman who had a heart attack. And I said, wow, very young. How come? Oh, she has poorly controlled diabetes and high blood pressure and cholesterol. Then I realized that, hey, those seemingly are the root
Right.
of the
Yeah,
issues.
they're the real.
So that's how I ended up trying to dive deeper and evolve from wanting to become a cardiologist to an endocrinologist.
Even if you had become a cardiologist, we wouldn't be speaking. Great to have you. Yeah.
Yes. And then in the practice of medicine, you realize that it's also not just all about medications. Metabolism is essentially a balance.
Right.
We have to be able to use the fuel, largely coming from foods, of course,
Yes.
right? And be able to convert that into relevant sources for energy, function, and growth. And that's when, if those processes are not regulated, we run into a lot of issues.
So maybe we start talking about metabolism by looking at what I would think is the hub of metabolism, right? The mitochondria, right? So and everything orchestrates around it for it to be able to produce energy. So maybe you can talk a little bit about the role of the mitochondria. What does it do in this energy production process?
So the mitochondria is a component in our cells, right? That is like the energy center. When we consume different foods, they get broken down into different sources of energy. For example, carbohydrate gets converted into glucose, fat or lipids into fatty acids, proteins into amino acids. And these are the building blocks or substrates that then go to the cell. And the mitochondria is the energy center that takes in these substrates and converts it into chemical energy that's called ATP or adenosine triphosphate to be then used appropriately for the various functions as needed. So a key component is the ability of our body to adapt. So then if you think about it, we are not static beings. We sleep, we move, we eat, we have to use our brains, we exercise, and we need to be able to adapt to generate the right amount of energy and to perform and function. So our body is actually a very sophisticated system that must process these different sources appropriately to generate the right type of fuel for us to use optimally. And so, as an entire system, different organs in our body, the brain, the heart, muscle, liver, fat, all may have different abilities to adapt these processes depending on what they are meant to do. So, for example, the heart is a critical organ, as we all have said, and it's a pump. It needs to then pump blood that carries oxygen and other key nutrients to every other body part. It cannot fail, otherwise, everything else could fail. So, the heart actually has to be able to use fuel in an adaptive fashion. And it's one of a unique aspect is that it actually would use more fatty acids than glucose. And it has the ability to use glucose, but under normal conditions, it would prefer to actually use fatty acids. And in fact, when you have heart failure, that optimal processes don't quite happen. And some of the drugs in development or that are used actually to treat heart failure help to correct these imbalance. So at the end of the day, at a cellular level, the mitochondria is the energy center, and it plays a critical role in different cells, tissues, and organs in the body.
And every organ, whether it's the heart and the liver, all of them have mitochondria.
Well, some cells don't. So, for example, red blood cells have no mitochondria.
Right.
Right? And they then have to use mostly glucose.
Mm.
So, actually, also the eye has no mitochondria.
Right.
So, that again is a very sophisticated engineering of sorts that has enabled us to function well as a system. Some of these things are understood, some not completely understood.
So coming to this interesting point, you said that there was a statement somebody made a while back that is the mitochondria which makes us older. Because it's oxygen what we breathe in, which burns the fuel. And it's oxygen which leaks as free radicals, distresses the body. So how much do you think the energy generation from mitochondria is responsible for deterioration of the body? How much of the mitochondrial function play a key role? Can we tweak mitochondria? Can we fix mitochondria? Can we slow down the mitochondrial burning? And that will bring me to the second question, which I'll ask you later: is that all calories equal, coming from protein, fats, lipids? How much of them affect mitochondria? Do they have different impact on mitochondria? Is there some which is a fast burner, some which is slow burner?
Right. Great questions. Let me start with the first part, right? Well, when it comes to the function of mitochondria, again, as with everything, it's optimal function. So there's no such thing as is it all good or bad. It is good it is essential, but the function has to be optimal. And if you think about it again from a systems perspective, if you overload a system, you could put stress and result in undesirable, unintended consequences. So, like I said, there are processes that we understand and there are processes that we still don't completely understand. And hence, the mitochondria remains one of the most intensely researched areas for a lot of scientists over the world. Uh, and then you can say, is it the quantity of mitochondria or is it the quality or the function? So when it comes to quantity, lots of researchers are trying to figure out, for example, can we increase mitochondria in fat? So brown fat is called brown fat because it has a lot more mitochondria. White fat does not have mitochondria. It used to be thought that adult humans don't have brown fat, that they only exist in certain animals and in infants, and that it used to be thought that they exist, for example, in the scapular region, right? But then a series of studies actually in the New England Journal of Medicine showed that indeed adult humans, and this was discovered serendipitously when they analyzed lots of scans from people who are undergoing scans for various other things in the abdomen, that they saw that there were areas that lit up that suggested the presence of brown fat because they are very active. And that led to a lot of intense research as well into whether we could manipulate fat to turn them brown. And it gets more complicated than that. There's brown fat, there's beige fat, but you get the idea. If we could try to upregulate brown or beige fat, perhaps that would help combat obesity, the problem where we have loaded the system with too much energy, more than what we need, and then we bank it perhaps with white fat, particularly bad white fat, visceral fat that can contribute to disease. At the cellular level, then there are also, for example, pathways that then people try to manipulate. For example, if you deprive it of oxygen and you can upregulate HIF or hypoxia-inducible factors, and then basically conceptually put the body under some stress, not too much stress, but just enough so that the body learns better how to adapt, such that it can then increase the threshold by which stress causes a breakdown in the system. So conceptually, that's some of the work researchers are doing to try to understand whether there are optimal ways to manipulate the system to further optimize it for improved function.
So there is a very interesting concept called hormesis, where you actually subject the cell to suboptimal or system to suboptimal stress before an adverse event. And they have found that even in anti-cancer therapy, if you give cancer cells a low dose of treatment before you give the bolus, they become resistant. So do you think our body also have hormesis for energy utilization? So if you start giving small bolus of nutrition, they can handle large bolus of energy sources much better than actually giving suddenly a large bolus of energy. How does the mitochondria see these things?
Um, I don't think I can do justice to say a simple yes, no answer to your question. I don't think we know enough about it at this point. But I think it's a very interesting conceptual framework that is very plausible, right? But we need to understand the devil's always in the details. Like, even as you try to perhaps load some stress to retrain or train up the system, are all stressors or loaders the same? Can it achieve the same thing? And when it comes to then sources of energy, I think that was your second question, whether fat or protein or carbohydrates, are there differences again in how that contributes to the response from the system? At the whole person level, actually, some of the research by my team in the university did show that, in fact, if you give individuals meal challenges, one that, for example, is high in fat, another group high in carbohydrate, another group high in protein. And these are standardized meals. And we give these standardized meals to individuals, perhaps at a different metabolic set point. One group who are obese and another group who are normal weight. We found that the normal weight individuals, regardless of what you load, they didn't seem to get out of balance. But in the obese individuals, protein and fat didn't seem to elicit unwanted pro-inflammatory and oxidative stress responses, but carbohydrate meals did. So it's quite complex because what you put in doesn't affect individuals, the whole creature in the same way. It really depends on the state of the whole being, and then different fuels can have different effects. So we're still trying to also understand those mechanisms better. And then part of that is translating it then into looking at what signaling pathways actually get regulated or dysregulated at the cellular level. So we would look at, I guess, some of the top cells involved in metabolism: fat, muscle, and liver. And that's still work in progress.
So maybe that's a good segue to look at what are the organs that are involved in this metabolic processes, and what governs them, right? What are the mechanisms that govern that entire cascade of events and activities after you started with the gut ingesting your food?
Right.
How does the whole system function from there?
Yeah. Okay. So after we eat, our gut needs to start working on breaking that food down. And there are already local receptors, even at the level of the gut, that respond to it and will release hormones. So, for example, gut hormones like GLP-1, GIP. GLP-1 stands for glucagon-like peptide 1. And some of you may be very familiar.
Very
because-
popular these.
Yes. It's been in the news a lot, right? But if we use that as an example, it then gets released, and you see how beautifully sophisticated our system is. It then signals locally to the gut to regulate gastric emptying, even how fast it moves and absorbs different foods, down to the lower gut, and also signals to the brain and regulates neurotransmitters to tell us that we're feeling full and satisfied. It regulates satiety and satiation. And then there are peripheral mechanisms as well. Thereafter, we know that it has beneficial, we think now, cardioprotective effects. So it has beneficial effects on the heart. There are GLP-1 receptors at the level of the heart that then regulate optimal substrate metabolism, whether it uses fatty acids optimally as fuel. And it also goes to the kidney. And we now know also that it has renal protective effects on the kidney. And at the level of the kidney as well, it needs to be able to.
And this is just one hormone.
And
There are
this
many
is just
such.
one hormone, exactly. And I just started with one hormone, right, to give you an example. And then you layer that onto lots of other hormones, because insulin also gets.
Yeah, so
released.
maybe that's a good segue. I mean, that's like the master regulator there, along with the pancreas, right?
Well, it is a very important regulator. So in that sense, you're right, that it is one perhaps of the master regulators. And with a lot of these things, maybe some people think, oh, so if it's doing something really important, we just jack it up, like GLP-1.
Yeah.
So let's just inject loads of this or take more of this if it's good. Insulin, oh, it's a master regulator. Let's just manipulate it.
Right.
And indeed, sometimes it's abused, right? Like insulin is also, because it's an anabolic hormone. For people who want to build up more muscle mass, they try to manipulate it. But again, that's the beauty of endocrinology. It's all about a balance. It's not so simple that more is better just because it's good. It's good because if it's in the right amounts at the right time, it's good. But if it's at the wrong amounts at the wrong time, it's bad. And I think that's why I have a job, and this platform has a tremendous role to play, because we need to continuously build on that knowledge base and help people understand, importantly, how to use that knowledge to translate it into meaningful applications. And it's not so simple as more is always better. Too much of a good thing can be really bad. Right?
So I'll have an interesting point which you said. So you've listed a bunch of organs which play a role. Coming from a very lay perspective, I ingest sugar in some format, I just carbohydrate. It goes to all the organs. And if you happen to be somebody who's not have a very good metabolism, in which order you would actually say from your clinical understanding the organ will start failing or start suffering because of this dysregulated metabolism? Will it always be that the pancreas will be the first, or the muscle will be the first, or the brain would be the first? What would be the first signs you would go for that the metabolism is haywire?
Well, if you are using the example of glucose, if you load someone who still has a very good state of balance, right, and has good metabolic health, you see that, for example, a young fit person, they can consume a very high glucose load, and you can measure glucose in their blood. Nowadays, you have continuous glucose monitors that can do that. You see that kind of disgusting. They have a very flat line. On the other hand, someone who doesn't have a very good body composition, they consume a little bit of glucose and it spikes. The glucose spikes are very, very evident. So the response is because when glucose goes in, the body will, then insulin gets released to keep the glucose levels within normal range. If one has a suboptimal body composition, you get more insulin resistance, particularly at the level of muscle and liver. These organs are not as sensitive to the normal actions of insulin, which is insulin stimulates a receptor called GLUT4 at the level of muscle that opens up basically the gates to take in that glucose so muscle can use it for energy and growth of muscle, for example. But if you're insulin resistant, those gates are very, very tight. And you need more insulin just to get the same amount of glucose in. And in diabetes, for example, where we know it's a condition where you get abnormally high glucose levels, is because the body tries perhaps to make more insulin to push it through those gates. But by that stage, the pancreas, the organ that makes insulin, is kind of burnt out. The factory is running out of steam and it can't make enough insulin, the key that opens the door, to let glucose into muscle. And then we run into trouble and we get potentially dangerously high glucose levels. So medications that are used for diabetes either often manipulate or improve upon this state by loosening those doors or producing more keys, or somehow altering that balance so it's a little bit more ideal to facilitate homeostasis and regulate glucose levels. So, Deepa, unfortunately, that was a very long answer because
So
it's not so simple, right?
there's one kind of pair of organs here that it'll be good for users to our audience to understand how the pancreas and liver work in tandem to maintain that homeostasis. So I don't think we dwelled
Yep.
into that.
So the pancreas has alpha cells and beta cells. Beta cells make insulin. Alpha cells also make glucagon. And glucagon is one of the sources or precursors able to release glucose. Now, you see, when we are fasting and we're not eating, our glucose levels never drop to dangerously low levels as long as we still have a healthy system. And that's because if your glucose levels are starting to run low, alpha cells then, one of the pathways, there are others, kick in and say, let's release more glucose now to keep it steady.
So the liver releases the glucose.
Well, then that also signals to the liver
Yeah.
to release glucose from its stores. It's predominantly glycogen stores at the level of the liver. And then that also releases some drips of glucose. And that produces then your fasting glucose levels. So in diabetes, for example, when that pathway is not well regulated, is because insulin puts a brake on the glucose production by the liver. But now when you're insulin resistant, that brake is loose and faulty. And you get more release of glucose from the liver even when you're not eating.
So that brings to another interesting concept of metabolic rate. So when you say metabolic rate, how do you would like to explain it to the common people. What is
Sure.
metabolic rate?
So-
How do we go about recording it?
Yep. So rate refers then to there's got to be a unit time to it, right? So it's the amount of energy that's released or turned over or processed over a certain unit time. So your metabolic rate consists of three components. Basal metabolic rate, that's how much energy is being turned over, right, and released, even when you're not doing anything. That's basal metabolic rate. That actually forms about 60% or more of our total energy consumption or needs per day. Then you have thermogenesis related to what we call postprandial thermogenesis, or food. After we eat, there's energy required to go break that down and process it, and all the sophisticated systems that we talked about. So that consumes typically another 10 to 20% at least of energy as well, right? And then there's energy due to activity. And that is another modifiable component. If we exercise more and we're more active, we actually will be able to increase that and result in a net energy deficit. And that's how people are encouraged, for example, to stay active as one way of regulating a healthy weight. So those three components work in tandem. The basal metabolic rate, since it's the largest contributor, right? How does that work?
Yeah.
That is related largely also to our body composition. Muscle uses a lot of energy. And so if we have a body composition,
So even in a state of when we are still and not doing anything, our
Yes.
muscles take up
uh,
energy.
it does, and our
Mm.
brain, of course.
Of course, yeah.
Okay. So brain actually is major of our energy consumption, even when we're sleeping and at rest. My son was very cute. There was one day I said I was working very hard and very late, and I said, oh, I didn't even exercise today, and I was wearing a CGM, and I'm like, oh my gosh, I'm running low, not dangerously, not hypo. I said, oh, I'm running low, and I feel it, like I'm energy. I'm like, I don't know why I didn't even exercise. And she's like, Mommy, it's because you're using your brain a lot, right? And your brain consumes the most energy. And I was like, oh yeah, 101. But definitely, if we invest though in putting in more muscle mass, we then achieve a higher basis metabolic rate. Aging, unfortunately, and as we all are very familiar, we say, hey, why is it that it's so much effort just to not put on weight as we age? Because as we age, particularly 40 and above, we tend to break down muscle. And when our body composition shifts and we have less muscle on us for the same weight, less muscle and more fat, our basal metabolic rate tends to go down. And it's a bit of a vicious cycle, because then that means we are more prone to putting on weight. And if we're not active and using our muscles, we may put on the wrong kind of weight and put on more fat. And then that starts a not very healthy cycle potentially. So the most common or most prevalent fat in adult humans would be white fat. But even white fat is thought to be not all the same or equal. Simplistically, white fat that's deposited around our organs, visceral fat, is thought to be bad. Whereas those that are under our skin, the subcutaneous fat, ironically, those that maybe we think are ugly as cellulite, is thought to be the good fat. And the bad fat is thought to be bad because they secrete a lot of hormones that are more pro-inflammatory, that we know can contribute to higher risks for blockages in the arteries, for heart attacks, strokes, etc. If you think about it from an evolutionary perspective, perhaps one of the key functions of fat is as a storage organ. But now we know it's not just a passive storage organ, it's actually an active endocrine organ as well. But as a storage organ, we want to store it as it also evolved to protect us, for example, from cold. And it also evolved to potentially protect us from damage. That's why there is fat around the vital organs. But if now we are in an era where there's a lot of surplus and the amount of fat is just overwhelming for the system, that is what's leading perhaps to a lot of the chronic diseases in part that we're seeing. And the interesting other concept is that different populations may have a different threshold for that. And that concept is called adipose tissue um, capacity or expandability. Simplistically, think about it a little bit like we all have cups in front of us. Unfortunately, our cup sizes that we're born with are not equal. So some of us are born with a bigger mug, and some of us are born with a little teacup. And so if you think about then water or liquid being poured into the cup as excess nutrients coming in and have to be stored as fat, the ones with a smaller teacup, it will tend to overflow and not be desirable. The ones with a bigger mug have a much larger capacity and seemingly able to store a lot more before they run into trouble. So these different thresholds also make a difference to how we store the fat, how much we can store, and not just quantities of fat, but now the concept that the quality and function of fat is critical.
So that brings to a very interesting point, quality and function. So India as a country has very interesting design evolutionary. We go through this famine and feast cycles. We get a lot of food and then suddenly there's no food. So, and we call, if you go by that design, Indians are not fat. Fat means contextually fat and obesity goes hand in hand. So we are not fat. So that means we are fitter. But interestingly, we are not. So how much is the weight of the fat in the body is actually linked to the health of the body?
Yeah.
You said white fat is bad. Understandably, and visceral white fat is bad. But how does visceral white fat affect our ability to be thrifty in terms of nutritional uptake? Does it really contribute to our ability to, work or consume, use it as a source of energy when there is famine or something?
So, Deepa, I think what you're referring to is the thrifty gene hypothesis. And that is related to the fact that our bodies evolved perhaps to protect us from periods of starvation. If we don't know when we're next going to see any fuel sources come in, we better hang on to as much as we can and adapt. So you might lower your basal metabolic rate to be able to continue vital functions, feed the brain, etc., even when there's not a lot of fuel sources coming in. But the trouble with that, as you pointed out, is that in our urban lifestyles now, we then go through, even within a day, periods of feasting. Maybe intermittent fasting that mimics starvation, and then feasting. But then our bodies then have lowered the metabolic rate, perhaps. And when the feast comes in at a lower metabolic rate, you then don't need as much and you'll store the excess potentially as fat. And the worst place to store it is around our bellies. There's a very high correlation between central adiposity and visceral fat. And that is why it is well known that actually beyond weight and BMI, which is a very crude indicator, you want to look at body composition. And if you don't have access to a fancy machine to assess your body composition, the cheapest way to do that is just to measure your belly. So what we call the waist to hip circumference. And that lends itself also to this concept of the apple-shaped body, where there's a lot of central fat, is not so healthy. The pear-shaped body, where there's more around your hips, is thought to be a healthier shape for health. Now, if you think about it, women tend to have pear-shaped bodies. Men,
Live longer.
yes, I guess we do. Women tend to live longer. That's just statistically the case, as we can see from life expectancy data all over the world. Yes, but there can be multiple factors for that, right? But yeah, perhaps one of the factors could be this. And why is it then that women have this fat distribution as compared to men? Obviously, we differ in our hormones, and we know that the female hormones, like estrogen, do tend to play a role in where we deposit our fat and regulate a lot of metabolic processes as well. And yes, that is actually, again, factually true that women are somewhat more protected from heart disease as compared to men up to menopause. And once menopause hits and the female hormones then are different and not so much at play, the increase in cardiovascular risk for women starts to catch up now with the men.
I think that's pointing to another important marker, BMI, right? And why the BMI thresholds have to be different for
Right.
different populations. And
Yeah.
you've worked with a lot of Asians and
Yes.
South Asians specifically. And
Yes.
in your 2-3 days in India, you would have noticed that there is this the standard Indian male is has a nice belly here, right? Um, so how do you look at the BMI thresholds for South Asian populations versus other
Yeah.
populations?
Yeah. Yeah. Well, if it's any consolation, it's not unique to India and Indian men. We know that the onset of metabolic diseases like diabetes and its associated complications, even heart disease, kidney disease, etc., occurs at lower thresholds, at lower BMIs
Right.
in Asian populations as compared to
What's that number?
Western. So if we look at a BMI of 30, that's what's considered to be obese. That's the WHO cutoff. In Asian populations, it tends to be ranging from 23 to 27, 28. And within that, if we break that down further, unfortunately, you are correct that South Asian or Indian populations have the same percentage body fat at a BMI of about 23.9 as compared to a Caucasian man with a BMI of 30. So clearly, you may not potentially have um, as much excess weight relative to your height, but the composition of that is much higher in fat. And yes, perhaps the deposition of that fat around the waist does lend itself then to the complications of metabolic disease and results in that lower threshold for the onset of these conditions.
Is skinny fat kind of the same
Yes, it's kind of the
phenomenon?
same concept, right? Where maybe on the outside, you think we look skinny, but actually on the inside, the unhealthy fat and the risk it poses to our health is very present. So, what does that mean? I think we have to tune ourselves a little bit more into it and definitely not be complacent that we don't look as fat, if we like, and that so we should be okay, but reframe our mindsets into maybe not being so fixated on weight per se, but a healthy body composition where we have a smaller waistline, more muscle in our limbs that lends to more stability and fitness as well, and protects us for the risk of these diseases for the long haul.
So, Sue, very interesting point you mentioned about the Caucasian versus the Indian or the Southeast Asian population differences. So let me ask you something very, very obvious. So what you're saying would say that we, as a Southeast Asian, have to work harder than a Caucasian to keep our body fit and metabolically fit, because we not only put on visceral fat, we also tend to put a visceral fat at a much lower BMI in a different form. That means while we do not put on muscles, we still need to work out harder to keep ourselves fitter.
Yes and no, because I think working harder is again a mindset, right? Um, One of the reasons I started Novi, um, as you mentioned, Prashant, I'm a clinician scientist. I'm very data driven, and understanding some of the fundamental processes that we talked about today is a firm foundation. But then we need to translate that into action, right? And I really felt that all that knowledge is useless if we're not doing our part to empower people to break down that knowledge into sustainable action. So, coming back to your point, hard work. I really I mean, through NOVI, we try to take away that hard work. It's about then maybe increasing the awareness and then reprogramming the system to make it easier for us to make the right choices for ourselves. So if you think about what food, we just talked about how different foods go in, how it's processed. We want to put in the right foods into our system, the right amount and the right quality. It's like if you're a car. If you're actually built as a high-performing car that should use petrol and you go and fill your tank with diesel, you wonder why it starts, it moves, and then after that, you're in big trouble, right? So simplistically, it's somewhat like that. It shouldn't be hard work. It should be about reprogramming and awareness and then shifting into sustainable habits that are good for us. It becomes like brushing our teeth every day. Sorry, one aspect though, as to why it can feel like hard work is because I think it's a very complex thing, the intersections between our genetic or biological predisposition and the environmental factors. And if you think about societies and populations that have rapidly urbanized, our lifestyles have changed so rapidly in less than one generation. We become a lot more sedentary. We work in professional jobs, perhaps, that sit in front of the computer and we don't move as much. We're always time starved and putting in foods that are readily accessible. And unfortunately, a lot of the foods that are in the food chain right now are maximized for profits. So there are a lot of empty, dense, very calorie dense, but nutritionally quite deficient and sparse. Right.
So I think it's related to a little bit of what we have spoken, but slightly a different concept and maybe a capability that one has or does not have. This whole idea of metabolic flexibility, pretty complex and not so easy to understand. So maybe you could throw some light on that. And how does
Sure.
one adapt or remodel oneself and become metabolically?
Yeah. So you actually answered the question in your question. You used the word adapt. So flexibility is about being able to adapt and being able to tune in for what you need at the right time and change what fuel source you use at the appropriate juncture.
But is there
That's metabolic
something in
flexibility.
our current, maybe how our metabolism is today, or how we've kind of built ourselves, that gives us the flexibility or denies us the flexibility, was my question.
Well, again, the concept of metabolic flexibility is that you are able to adapt, and that means that you should have, again, the optimal balance of, again, coming back to body composition and the concept of metabolic reserve is related to insulin resistance, having the right amount of muscle, a proportionate amount of fat, and so on. It's all about achieving the right balance. And that enables us, again, to be flexible or nimble, to be able to have the right systems in place to be able to respond to what fuel is needed and change, activate those switches at the right time. There are things that we can do to train it. So, for example, if we are starting point don't have enough muscle, just work towards changing your body composition to building up a little bit more muscle. And then, of course, within muscle, there are different types of muscle groups. And then you can revise your goal to say, actually, should I be trying to bulk up or should I be trying to increase just my lean muscle mass, even without a lot of muscle bulk? And those then get down to a very hyper personalized, I would say, right? Tweaks that one needs to make that is constantly evolving depending on how you're changing. And then it also is semi-dependent on what else you're doing, whether you are sleep deprived or whether you're well rested, also affects how adaptable your body is. And we know sleep as well plays a critical part because it's well documented as well. In periods of sleep deprivation, insulin resistance goes up. So it's a complex interplay, but very logical at the end of the day.
So great. So I think we have kind of covered most aspects. It'll be good to do a quick summary of the aspects of metabolism that we spoke about today, the organs, the mechanisms, uh, and everything
Sure.
around that.
Sure. Yeah, we covered a lot of ground today, right? We started with what is metabolism, and we said that's about achieving an optimal energy balance. We talked about that at the level of the cell, at the level of organs, and at the level of the whole system. And I hope it's now clear that metabolism and maintaining good metabolism, metabolic health, to be metabolically healthy is a key foundation to healthy longevity. If you think about it using a house as a framework, that forms the foundation of your house. Then you have key pillars. We talked about heart disease being a number one killer. That is the pump in your house. You got to keep that well oiled, well functioning, and that relies still on a solid foundation. Then you have key other things like vascular system. Those are the pipes in your house. Gut health, we didn't have a chance to dive into that very much, but we did talk also about how it's a complex interplay where the gut also releases hormones. So that's another pillar where that's also another pipe in your house. And then we went into a little bit about immunity and repair systems and how when that goes wrong, or is not well regulated can contribute to development of some cancers as well. And we also talked about the musculoskeletal system, which is the scaffolding in your house. So metabolism and metabolic health forms the foundation, and there are all these numerous pillars. Last but not least, you have the brain, which is the roof of the house, an incredibly sophisticated organ that caps everything off and perhaps is also a master controller of the house. So many things to unpack, but it's been a wonderful conversation today.
Thank you. Thank you, Deepak.
Thank you, Sue.
So see you on the next episode. Look forward to the next episode where we will discuss the idea of homeostasis in the glucose mechanisms in your body. And we will also look at what are the drivers that will help you maintain this homeostasis. Look forward to seeing you in the next episode.